All right, we are going to finally sketch a proof of the existence and uniqueness theorem. So I have copied from the previous slide the definition of our Picard iteration scheme. So I copied this business right here. This is our Picard iteration scheme, and I've copied it over here. And all I've done is I've decided to give it a name, capital G. And capital G is a function on this metric space of functions. So phi is a function in this metric space of functions. We're going to denote our metric by like this, using what I called that norm notation, so double absolute values. So I'm not going to use the letter D. That is going to be our metric. And I'm not going to define what that is, but it's something like the supremum of the distance between those points, between the points of the function. That's one way you could do this. There are other ways you could do that. Right? So just note that, right? So what we want to do, our goal, I shouldn't have made that go away. Our goal here is to show G is a contraction. And if G is a contraction, if I can show that this is a contraction, then that means it has a unique fixed point. But we know that fixed points of this correspond to solutions to the differential equation. And so so that unique fixed point of G corresponds to a unique solution of the given initial value problem. Right? That's the whole game plan right there, to show that G is a contraction. If we can do that, boom, we've proved the existence and uniqueness theorem. And we will do that with some hand waving in there for a couple of things that get difficult. But really, I'm looking at my notes, and it's 1, 2, 3, 4, 5 lines. So that's not too bad. All right, so let's go on with this proof. All right, so what we're going to do is we're going to compute. It works better if I can do this. I can write smaller. We're going to compute, except I can't write very well. We're going to look at the distance between G of phi and G of some other function, i.e. point psi. I'm going to write that what that is, and that is going to be the norm. Well, let's just think before we start writing down. So we're going to take phi and put it in here, and we get this, exactly what we see here. When I put psi, that other function, in there, I get the same thing, except that now becomes a psi. And then I subtract them, and when I subtract them, the x zeros go away, and then I can combine that all into one integral. So I'm just going to, so I get the integral from t0 to t of f of s phi of s minus f of s psi of s ds, and then the norm of that. Right? So again, what just happened there? Not a whole heck of a lot. All I did was subtraction, and when I subtract, the x zeros cancel out. And because we're subtracting, I can combine those two things into one integral. The next step now is to bring the absolute values, or the distances, inside the function. When I do that, I'm going to do two things. I can do two things. One, there is a theorem that says the absolute value or the norm of an integral is less than or equal to the integral of the absolute value or the norm. This showed up in complex if you've had 321. This shows up, we mentioned it in Calc 1 and Calc 2, that we don't use it very much there, but we're going to use that here. So I'm going to bring those inside. And also when I do that, I'm actually going to change from these norms to regular plain old absolute values. And that's one of the places where I'm waving my hands. So this is now becomes absolute value of f of s, comma, phi of s minus f of s, comma, psi of s, close parentheses, close parentheses, close absolute values, ds. Again, what the heck did I just do? I just brought the absolute value inside, and that changes the equality to a less than or equal to. So I did that at some cost. I no longer have equality there. Now let's look at this, at where we're at here, right? And what we ultimately want to get here. What I would really like to get, where I want to end up, in fact, I'm going to write this on here in red, where I want to end up. I want to end up, if we scroll down, ultimately I want to end up with something some constant times the distance between phi and psi. Right? So why do I want to end up with that something's a constant? So why do I want to end up there? Well, remember, we're trying to apply the contraction mapping theorem. And so what I want to do is I want to look at the distance between g of phi and g of psi and compare that to the distance between phi and psi. So that's where I want to end up, right? So let's look at the integral that we have in front of us at this one step and ask what in the world we have to get rid of to be able to do that. What do I need to strip off? Okay, so there's a couple of things. The most obvious thing that has to be stripped off is the integral. That somehow has to go away because there's no integral down here in red, right? So somehow the integral here and the differential have to go away. The second thing that has to somehow go away are the f's, right? And I don't really need to make the absolute values go away because that is a distance measure. And again, this is the place where I'm waving my hands, going back and forth between distances between functions in the function space and distance between numbers in R. So I need to make the integral go away and I need to make the functions go away. And I'm actually going to work from inside out. And I'm going to tell you how I'm going to do that. So the first thing I'm going to do here is going to make the f's go away. And so I'm going to write this down. Not in red. I want to go back to blue. This is going to be less than or equal to the integral from t0 to t of some constant m times the absolute value of phi of s minus psi of s, close absolute value, ds. And I'm going to tell you what I just did there. I'm not just going to make that happen. Where did that come from? Okay. I claim that this follows from the mean value theorem. Right? And so I'm going to remind you of what the mean value theorem says on the next page. And I'm going to do an inequality. It's easier. The mean value theorem relates the average rate of change of a function in R to its instantaneous rate of change. So it says, and when we write it as an inequality, that f of x minus, well, usually we write it this way, that f of x over x of y divided by the absolute value of x minus y is equal to some constant c that turns out to be the derivative at some point in there. It turns out to be a derivative, so that's f prime of c. If I multiply both sides by x minus y, I get f of x minus f of y, absolute value. On the right side, we get c times x minus y. And if I change that, I can change it to a less than or equal to, and say where c is equal to the maximum of the absolute value of f prime of x on our given interval a, b. So it says, and so that's what I've done, is that's the mean value theorem, and that's what I just used in the previous page. Except that S, what I called C there, is now an M. And yes, that function f depends on both s and the function s and x, but the mean value theorem can be used in that context as well. So that was just the mean value theorem. And m, so m is not necessarily less than 1. M could be 100. If that function is really steep, that m could be really, really a big number. I don't know what it is. It's just some constant m. All right. So that's for some value m. All right, so now I claim that this is less, oops, wrong color. I'm having trouble, I'm color challenged today, back to blue. This is now less than or equal to. Now it's time to get rid of the integrals. In fact, let's go back and do this again. Let's just think about, let me delete this business, and let me talk to you about let me remind you something about integrals. Please go away. There we go. Okay. So if I do the integral from a to b of f of x dx, you know that that is the area under this curve. That is less, so what is the absolute worst approximation we could make of that? And you also know that we got that by adding up areas of rectangles, right? So what's the absolute worst approximation that we could make? How many rectangles would we take? One. We would take one rectangle and we would define its height some way. If I want to make an overestimate of that actual integral, I would take the maximum value of that function, and then I would make one rectangle at that height, and I would approximate with this rectangle here. It's a pretty crappy picture, but I think you get the idea. And I'd say, well, that's less than or equal to m times the distance between a and b. So m times b minus a. That's called the mean value theorem for integrals. Again, or mean value inequality for integrals. And that's all we're about to do in this next step. So this now is less than or equal to m, and that makes notice that made the integral sign go away, m times the width, which in this case is t minus t0, times we took the maximum height, but for us, that's simply that turns out to be the absolute value or the magnitude that we get from our norm is their wavy, hand wavy business of phi of s ds. That's what I called m in that last thing. And now look what I just have where I ended up. Where I ended up in this line right here is the form, almost the form that I want, right? I now have that g of phi minus g of psi is less than or equal to something times the distance between psi, phi, and psi, which is exactly what we want. Except I need to make this thing less than, I need to make this small, right? This, I need m times the quantity t minus t naught to be less than 1. So how can I make m times t minus t naught less than 1? That, I can do that by taking t close to t naught. So now I can say that there exists an epsilon greater than 0 such that m times the absolute value of t minus t naught is less than or equal to mu, which is strictly less than 1, for all t in the interval t naught minus epsilon to t naught plus epsilon. And that right there is where the local part of the theorem comes in. This is why the existence and uniqueness theorem is a local theorem, because I have to do that step to apply the contraction mapping theorem. And thus, by the contraction mapping theorem, G has a unique fixed point x star of t, and hence a unique solution to the given initial value problem. And we are done. Right. The only part of this proof that where I was not completely honest with you were two parts, and they had to do with the double absolute values versus the single. So the time that I switched from double absolute values to singles going here, that was hand wavy, and then when I did it back at this point here, that was hand wavy, and it depends on the definition of whatever that metric is on this space X. But the mean value theorem, the mean value theorem for integrals, those things you've seen before, this logic at the end should make complete sense to you. And that is the proof of the existence and uniqueness theorem. I got one more sort of fundamental result that I want to prove, and I will do that in another couple of lectures. And then we're going to finish up this semester talking about the Lorentz attractor and chaos. And so that'll be really fun. All right, we'll see you. That's enough for today.